Welcome back, students. Today we're talking about trigonometry, functions, and their friends, at least how to write them. Remember to code switch into Nemeth for all of these parts of math. Whether it's a simple trig function written or a full tactile graphics of a function, go ahead and switch into Nemeth mode before it and make sure all of your math, including all of your graphics, are in the Nemeth mode. You won't have to make any graphics for this worksheet, but since this is our last lecture together, I wanted to make sure to talk about them because they are a pretty important part of how we communicate and understand math concepts. A review of some of the modes and indicators from the past few weeks. Remember, if something is written directly over, you'll use dots 1, 2, 6. If it's directly underneath something, it'll be 1, 4, 6. That multi-purpose indicator dot 5 can either start a series to be modified or end a superscript. And the multi-purpose terminator 1, 2, 4, 5, 6 will end a set that's modified. For some function names, you'll have a modifier above or below them that will need to use that 5-step modification system that you learned before, where you start with a dot 5, then write the thing to be modified, then say whether you're going above or below with the modification, put all of the things you're modifying it with, and terminate it to finish that set and move forward in the equation. Kind of a simple review as well of square roots. Remember, your square root radical goes the other way. It's dots 3, 4, 5. Whatever's in the radical comes next, and at the end of that vinculum, that line across the top, that's where you put the terminator, so that multi-purpose terminator can serve another way to terminate something, can terminate the boundary of a square root. If your root has a different base than 2, if it's not a square root, maybe it's a cubed root, maybe it's an nth root, then in front of that radical is where you would put the number, and in front of that, the opener for it, which is the same as our directly over symbol. And that makes sense because usually the 3 or the little n is written up above the check mark part of the radical. So there's like a 3 directly above the radical sign. That's the logic of how those go together, if that helps you remember it or recognize it when you see it. So, trig labels. They follow their own special spacing rule, and that's really the thing to follow this week. After any trigonometry symbol, or really after any labeled function, there's a space before what that applies to. That will include things that are like sine, cosine, tangent, cosecant, any of the different versions of that, but also the angle measure, like the angle symbol where you're measuring angle M. Or log, logarithm, base, whatever, or the natural log, which is written ln, or even limits. So any of these functions follow this pattern. There has to be a space after the word that tells you what function to apply before the thing you apply the function to. So here's some basic examples. We've got the sine of x. Remember, we're going to be writing this in a Nemeth section. All of our trig functions go in the Nemeth passage. You cannot write these out in UEB in a document that's using Nemeth for math. And also remember that under the new rules for code switch, when you switch into Nemeth mode, it's going to abandon all of the old Nemeth rules that allowed contractions. So we're not going to use the IN contraction in sine at all anymore. And so you don't have to figure out the subtlety of when you can use it and when you can't. If you have an old math textbook floating around your school that's in the Nemeth code or in Nemeth and eBay, that old Braille, you will see sine sometimes contracted. It will be contracted whenever it's not in numeric mode first. When we write it now, though, we're just going to write it spelled out because of our code switch indicators. That's part of the UEB rules affecting Nemeth. So sine of x will be sine space x, S-I-N space x. If the print does not have a space there, you might need to either do some sleuthing or check with a math teacher to find out if that's the variable. There are some other less common trig labels, especially ones that end with H, that you might not recognize as whether or not it's part of the variable or part of the trig function, so it's important to be able to tell that. But when it's written in Braille, you can always tell because there's always a space. The tangent of x, notice that we follow the system in the print for the capitalization of tangent, and we follow whether or not the term is in parentheses, but we still insert that space after tan, after the function name, before what it applies to, the x in parentheses. For the angle measure of m, same deal. You're going to use that angle symbol that you have learned, the shape indicator and the left pointing arrow, a space, and then the name of the angle to be measured. If you're measuring the degrees of an arc, there's a special symbol for that. You'll notice it's the angle symbol and then a shape modifier and then the arc symbol. Put a space after that name, even though that name is a pictograph. Put a space after that shape that is a function, and then the B that it applies to. When a variable comes after a function name, it does not require an English letter indicator in Nemeth. If the variables that come after a function name mimic a short form word, maybe you're measuring angle AB, it does not need an English letter indicator. One of the special rules of functions along with that space is we know we're solving a function. We expect variables to be coming. You will not need an English letter indicator here. These could also be used in a sentence. So I have an example. Page 74 shows the angles in the shape. In this case, it's not angle S. S is plural. It's part of angles. So even though I switch to Nemeth mode to show that angle symbol, the S is right after it, and that tells the reader that the S is part of the name, not page 74 shows angle S, because that's not what it says. It says it shows the angles in the shape. And so you can do that kind of funny pluralization stuff to these if you need to. And that spacing makes it totally clear which one is written. Students don't have to be in doubt. Combinatorics functions may not have come up a ton in this class or might have been glossed over last week. So if you didn't catch them, in combinatorics we often have kind of a leading subscript or a lower line that's in front of the letter. Here's how that looks. You would start off just with the subscript indicator and then whatever letter comes first, followed by that .5 to bring you back up to baseline before you write the regular baseline letter, which is often capitalized in combinatorics, and then subscript after it for the letter that comes after it. C sub n comma r is another combinatorics way to write. You're choosing something, you're choosing n out of a set of r items. It has the same kind of mathematical meaning, but it's just another style of writing it. Braille it however it's written. And so there's an example here too of the big C and then the subscript n comma r. Does anything look odd there to you? Did you spot it? The comma in C sub n minus r is not a comma you're familiar with. That comma is because the rule says that the effect of a level indicator is terminated by a comma, unless the comma occurs in a long numeral, like 100,000. If the comma comes between two separate items in a superscript or a subscript, the special symbol .246 must be used to replace the comma, or the comma and a space that's normally seen in Nemeth. That way, .246 does not terminate the subscript, and you can write multiple things in a subscript without it terminating and without it being confused as being a capital letter at that point. So if you ever see that come up in math class, now you'll have a chance at recognizing that that's just another way to write comma. Remember, if you are a TVI, use your problem-solving strategies. If you have a kid's Braille textbook and you see a symbol you don't know, Look at one of the sighted kids' print textbook, see what the print says, and see if that jogs your memory that you've either seen this before or that you can see it happens 22 times on that page, and so you can be sure that that's how you Braille the print equivalent. It's always okay to say to a student, wow, that rule seems to be an exception. I think I better go look up why this exception is used here. You can do that, but you can also figure it out if you've got the Braille copy and the print copy of the textbook available. All right, back to our regularly scheduled program. More on function labels. Remember, the rule is after a function label, there is always a space before what it applies to. That does not mean that there's always a space in front of it, only after it. There might be a space in front of it if there's a sign of comparison in front of it. There will not be a space in front of it if there's anything else that is normally unspaced on the front end. So cosine of x, again, cosine space x. What if I had 3 cotangent x? Then I would start off with the 3. I'd need a numeric indicator because I'm at the start of a line and nothing has started numeric mode yet, so numeric indicator 3, and then I'd write the COT for cotangent. Notice there's no space there. After cotangent, after that function label, there is a space before what it applies to. Why is there this space? Because it makes other things that work in Nemeth work in function labels. A common example would be logs. Logs often have a base, and really any function might have a subscript after it. So if I have log base 3 of e, and I'm going to calculate what that is, convert it into log 10, then I can write log with a 3 after it, and because our rules of superscripts and subscripts have told us that when there's a single number following letters, it's assumed to be a subscript because otherwise it would be at the front. That means I don't need a numeric indicator and I don't need a subscript indicator. I save 2 cells on doing log base 3 as just log 3. You read it as log base 3. It's understood that that 3 is written down below, but we don't have to waste the cells on it. And then when I put the space, I know that I'm writing the E that my log base 3 applies to. So having that space lets us use our regular shorthand and makes a lot of high-level math much more efficient. Another common example of functions is one you'll see in pre-calculus and calculus, and those are limits. Limits talk about how a function behaves, how a graph behaves, as it gets closer to a number. So what's the pattern of behavior here? The limit as x approaches 1 of 1 over x is how you would read, is how a mathematician would just normally read this equation, and is basically also how you would read it in math speak to somebody who's trying to understand it. To put it together, we're going to use that 5-step modification. Dot 5 at the beginning. What's being modified? The function name limit. So I'll put limit next as my step 2, LIM. Step 3 is tell us, are we going above or below? So you look at limit and say, is that x approaches 1, modifying limit above it or below it? It's written below it, so we use the directly under indicator for step 3. I've got that in dark blue here. What's written underneath is x approaches 1. X approaches 1 is done with kind of that short arrow, and that short arrow is a sign of comparison, so it gets spaces on both sides of it. Once I've got everything that's written underneath, then I'm going to end it with my multi-purpose terminator, that ER looking thing. And after that, I can put the space, and I have to put the space there, and the space is missing from this slide, so I'm going to have to fix that. Space after the multi-purpose indicator, and then write your fraction with the fraction indicator 1 over x, and close that fraction. There are some other tools for teaching visual spatial content. Of course, with little kids as TVIs, we are always going to start with real objects. Teach young kids triangles and squares and circles and all their basic shapes with real things that are those shapes. Then, for tactile graphics, work from low tech to high tech. You'll want to use tactile graphics that are modifiable, things you can change as you talk about them with the student, as well as static tactile graphics, like regular worksheets that have a circle on them when kids count the circles. Get good at those basic tactile graphics before moving to auditory representations of them, because we want the concept in place first. I have examples here that are, if you've not seen them, the first one is APH graph paper, which is pre-printed with X and Y graph lines on it, and then WikiStick stuck on it to show the shape of a graph. The second one is a rubber band board. I'd encourage you to use latex-free rubber bands if you're working in school settings. There's often medically fragile kids who are allergic to latex somewhere in the classroom, so best to just keep them on the latex-free side. But these pegboards have lots of raised pins on them, and you can stretch a stretchy band around to draw different shapes or to plot along certain points of a graph. So it's a very interactive way for kids to move it. If they calculate that the function crosses 2, 2, and then 3, 6, and then 4, 10, they can stretch their band to each of those points as they go and plot out the graph that way, and then be able to tactily feel what its shape is. And then the other two are higher tech versions. One is a tactile graphics display. It's a whole big page of refreshable Braille dots that are spaced evenly instead of spaced as Braille cells so that they can make graphic images. They'll raise to 4 different pin heights, and so you can make different textures and images that way. And then the last one is a talking calculator with an audio output on it, and that will change its pitch as you travel along a graph, so that you can hear the graph go woo, woo as you move along it. And so you can hear the shape of where it dips, where it rises, where the maximum is, where the minimum is, and then get it to talk and tell you information about points as you navigate it. So that's a great tool for high schoolers in math. When their peers are using a graphing calculator, they would use a talking graphing calculator as a supplement. That is also often being replaced now by things like iPad apps and computer apps that do the same function, but on a device the student's already familiar with. Some more examples of static tactile graphics you might make in a math class. These examples are made on a photocopy of the worksheet that's been put on swell paper, and then the numbers and letters have been replaced with Braille numbers and letters and then swelled in a PF or a pictures in a flash type machine. The middle one is protractors and angles that have been drawn on sheets of plastic in a tactile way, so they've been pressed and raised. And these are just some ways that worksheets might be adapted for a mid-level math class for kiddos who are Braille readers. As you're doing your homework this week, the point is to pay attention to the spacing. You will not have tactile graphics to make on this one, though you might want to know about tactile graphics for your final projects. As you're modifying and adapting assignments, make sure that your blind and low vision students have access to not only the text of the lesson, but also any images that appear in the lesson. It's so important for concept development to have the whole picture and not just the narrative description of it. So that's why I wanted to make sure you saw these examples this week before you get to the wrap-up final projects in class. Until next week, happy Brailing! See you online.